All right, so we just looked at that infographic where we talked a little bit about catalysts and how they speed up the reaction by simply lowering that activation barrier. I want to dig in a little bit deeper and look at some of the concepts that really talk more into the mechanisms by which chemicals interact. And so you know what reactants are, you know what products are, you know that a chemical reaction is going to depend upon the orientation it would take for stuff to collide. What I want you to think about is if we have this reaction right here, what has to happen in order for this to occur? Well, you can see that you need 4 hydrogen bromide molecules and you need 1 oxygen molecule. Can you imagine how slow it would be if we had to wait for all 5 of these molecules to collide at the same place, at the same time, with the pretty, orientation that they need in order to react, and with enough energy to overcome any energy barriers in order to react? That would take forever. And yet we know that that's not actually how this happens. It actually happens in steps. This is sort of the idea of doing small steps or small chunks, whether it be studying for an exam. You're not just going to bite it off in one piece. You might take it step by step to slowly overcome the barriers that are in front of you. That's what reactions do. They happen in steps. And so what we see here are some steps that are used to create this reaction. And so instead of 5 molecules coming together at the same time and place, etc., we have 3 steps that are used to accomplish the same overall reaction. Now, how does this work? Well, first off, if you look at step 1 is creating this molecule, and then step 2 takes that same molecule and reacts it with hydrogen bromide, thus destroying it. So since it's on both sides of the reaction, it's going to cancel out. Similarly, in step 2, we have this molecule being created, and then in step 3, it's good to go away. And so we can cancel it out. And so if that's what happens, all of those are called intermediates, where an intermediate is anything that is created. It has to be created. And then it's transformed or destroyed, not really destroyed, because, law of conservation of mass says matter is not created nor destroyed, only changed in form. So transformed is a much better word than destroyed, okay? It's never present at the beginning. It's never present at the end. It's created and then consumed or transformed. And so anytime you see that, those are your reaction intermediates. So the things that I've highlighted here, those are reaction intermediates. And so because of that, we can now look at all of our steps, leave out the intermediates, okay? Ignore them, pretend they're not there, and just bring everything down. So meaning I have 1, 2, 3, 4 HBRs, hydrogen bromides, plus 1 oxygen, to yield 2 waters and 2 bromine gas molecules. Is that the same as the final reaction here? Absolutely. And so instead of it all happening in one step, it's happening in multiple steps. And because of that, we can then learn a little bit about the rate. Notice how it says slow, fast, fast. That would have been determined experimentally. And so what's called your rate determining step is going to be the slowest step in the reaction. And so notice how we have this right here, the rate determining step, and I'm going to call that the RDS for short. And so what would be the rate determining step in this above example? It's number 1. And so how do we determine the rate? How does the reaction rate relate to the rate determining step? Well, if our reaction for number 1 is hydrogen bromide plus oxygen yields HOOBr, then that tells us that our reactants are what is going to be used for our general rate law. So remember, we have rate equals K times any of the species that the rate depends upon. So in this case, it's depending upon HBr singly and oxygen single as well. And so this is what's called a bimolecular reaction. And that's just simply because we have two reactants that are reacting together to form the product in the rate determining step. That's the important part. You cannot just look at this right here and say, oh, HBr must be to the fourth and oxygen must be to the first. No, no, no. You could only do that if you look at the rate determining step. And so for each of these, you look at it and then you determine the molecularity, and your rate law is going to be proportional to the substances, the reactants in the rate determining step. So like this would be rate equals Ka to the first. Here it might be rate equals K times A to the second because there's two of them. Here is rate equals K times A to the first, B to the first. Here your rate equals Ka to the third, and so on. You get the idea. All right, let's use what we learned from above and consider the following reaction mechanism. The first thing we want to do is write the overall reaction. So go through and cancel out any intermediates. What is actually our intermediate in this reaction? Try and identify it now. You should have identified fluorine because fluorine shows up as it's created first and then it is transformed into something else. And so it's going to get eliminated in our reaction. And now let's just rewrite it because nothing else has been created and transformed. So we have 2 nitrogen dioxides plus fluorine gas yields 2 NO2F molecules. That is our overall reaction. What is the rate law for this reaction? Well, remember, you first have to identify the rate determining step, where your rate determining step is simply the slow step. And then you look at the reactants, and you use those reactants to identify your rate law. So your rate equals your K times NO2 to the first, because it has a coefficient of 1 times fluorine to the first as well. And so if we look back at what kind of molecularity it has, it's going to be bimolecular. And so it's a bimolecular rate. All right, so that is kind of how you do it. You figure out what intermediates are. You figure out if there's any catalysts. We're going to look at catalysts in the next step. And then you rewrite it, and then you base the rate law off of the rate determining step. But before we do that, let's look at this figure on the right. So it says, how does the figure to the right, which is a potential energy diagram, relate to the rate law for this reaction? And so the idea here is notice how large this activation energy barrier is compared to this one. And so the idea is this one is so much larger, therefore it's a larger hill to climb, and therefore it is the slow step. And so the idea is typically there's a larger energy barrier for the slow step, for the rate determining step of a reaction. And so keep that in mind. Activation energy is directly related to chemical mechanisms or chemical steps. All right, let's do an example with catalyst. A catalyst is anything that speeds up a reaction in order to make it more favorable. The important part here is it can't be created or destroyed in the elementary steps, meaning it should be present at the beginning of the reaction, and then it must return to its original form. It has to be present at both the beginning and at the end of a reaction. So you're looking for something that's in the beginning, and you want it to end up in the end as well. And so for this reaction, what is it? Is hydrogen present at the beginning and the end? No. Is palladium? Absolutely. And so palladium is our catalyst. So PD equals catalyst. And so this is a palladium catalyzed reaction mechanism. Is there anything else that we can identify? How about in yellow? Let's go ahead and identify any reaction intermediates. And so here you can see PDH, and then we have another PDH on both in reaction 2 and 3. And so it disappears. And then C2H5 disappears as well. And so what that does is that leaves us here at the bottom with a H2, a hydrogen, plus C2H4 yields my C2H6. And so I have intermediates that I got rid of, and my catalyst also canceled out. But whether or not it was originally created or not is what identifies it as a catalyst. And so notice my catalyst is present as a reactant in step 1, whereas my intermediate was created first and then transformed second. I guess that could be how you would also write your catalyst, is it was destroyed first, not really destroyed, but you know what I'm saying, destroyed or transformed first and then created second. Okay, so the order matters. But with that, you're able to identify reactants, products, intermediates, and catalysts in a reaction and determine the general rate law from a reaction mechanism by identifying the rate determining step.